Okay, hello again. I'm Josh Bongard. I'm the instructor for the Evolutionary Robotics MOOC called Ludobots. If you're new to the course, the URL is here. This is also office hours for CS206, Computer Science 206 here at the University of Vermont, Evolutionary Robotics. So I will be online from now, 3 o'clock Eastern Standard Time for the next hour. If there are any UVM students or online students that have any questions, go ahead and ask it. Go ahead and ask it in the Twitch chat room here, and I will do my best to answer any questions that you might have. Okay, so again, I will answer questions throughout the hour. Most of you are working on are hard at work on your assignments, so you may not have any questions. In that case, I will spend what time we have today introducing a new evolutionary algorithm called a steady state evolutionary algorithm. And this steady state evolutionary algorithm will pave the way to a more powerful type of optimization method called multi-objective optimization. So if you're evolving behavior for your robot, for example, and you would like it to move as quickly as possible, but also use as little energy as possible, you have two objectives, speed and energy efficiency. How do we create an evolutionary algorithm that improves both the speed of our robot and its energy efficiency? In order to do that, we will need to use multi-objective optimization. And if I have time today, I will talk about that. Okay, again, for those of you that are joining us, this is the office hours for the Evolutionary Robotics MOOC Ludobots and CS206. Okay, let's talk a little bit about the course first. As I mentioned, the URL, we host the MOOC out of Reddit, so it's www.reddit.com/r/Ludobots, and you can find all the information and all the material for the course from here. There's a stickied post at the top for those that are new. This stickied post has a number of pointers into the course at different locations. So if we click New Start here and scroll down a little bit, you'll see that there is a schedule for the course. If I click on here, this will bring up the schedule for the course and show you where we are and where we're going. Okay. So let's scroll down to today. We are at Monday, March 6th. So last week we completed our lecture on legged locomotion. And tomorrow morning we will be starting in on our lecture on bipedal locomotion. And we'll also be starting on assignment 8 of 10. So again, for those of you that are joining us for the first time, this course has in its backbone a series of programming projects. This is a visualization of the course as a whole. Here's the starting point of the course. As you go through it, you implement a series of programming projects, and then when you finish the last or the 10th programming project, you create your own final project and evolve your own robot to do something new. So currently at the course, most students are at assignment 8 of 10. And if I go back to the main page for the course, again, there's a stickied post here. If you click, you can get started immediately here. We are following, in this year, we are following the Python-only track through the course. You'll see there's a whole bunch of programming projects here, and you implement one after the other. Okay, so most of the students are on assignment 8 at the moment, which is the parallel hill climber. And next week, assignment 7, the parallel hill climber. Assignment 8 will be assigned tomorrow, which is the quadruped, which I can probably show you here. We've seen this a few times if you've been following this course so far. We've got this robot that is a 4-legged robot walking around in this virtual environment. Okay, that's assignment 8. Assignment 9 is to implement a genetic algorithm. And then the 10th and final assignment is to evolve your robot in multiple environments, and these multiple environments contain a light source at a certain position, and the robot will evolve to walk towards that light source, regardless of where that light source is placed in its environment. That's known as, that behavior is known as phototaxis. So you'll be using a genetic algorithm to evolve your quadruped to exhibit phototaxis. And as some of you have probably discovered by now, those of you that have gotten this far, that the genetic algorithm in its basic form is a relatively weak optimization method. It's relatively difficult to get a robot, to evolve a robot to successfully exhibit phototaxis. So today, while I'm waiting for any questions, I will walk you through implementing a more powerful evolutionary algorithm known as multi-objective optimization. Okay, so let's start with step one, which is the steady state evolutionary algorithm. And before I implement it, let's write out some pseudocode of how this algorithm works. Steady state evolutionary algorithm. Okay, so why is it called steady state? Well, in the genetic algorithm, I'll switch to the whiteboard here so we can have a look at some, I can draw how this works. In a genetic algorithm, or GA, just make sure that you can see that, we have a population of individuals, population I1, I2, through population individual individual n. So we have an n individuals that are stored in a population. And this is generation 0. At generation 0, we create n random individuals. At the next generation, some of these individuals die off. So for example, individual IN does not make it to the next generation. Some individuals survive. So I1, assuming it has relatively high fitness, will survive into the next generation. And it might also produce offspring. So let's call this I1 prime, I1 double prime. Maybe it's producing some offspring. And again, we now fill up. Maybe individual 2 also produces an offspring. We have a new population at this new generation, and we continue this process for m generations. So a genetic algorithm is a generational evolutionary algorithm because it's updating at one generation at a time. The steady state evolutionary algorithm, which we're going to introduce today, we have is much simpler to start with. We have our population as before. We have n individuals like before, I1, I2, IN. And it's steady state in that at every iteration of every point in time, we select 2 individuals. Let's say we pick I1 and IN, and we compete these 2 individuals against one another. Let's imagine that this example, I1 has lower fitness than IN. So IN is the winner in this competition and I1 is the loser. We delete I1 and IN is allowed to produce an offspring, IN prime. Okay, so we just updated one small part of this population by picking 2 individuals at random, and we just iterate again. So now we pick by chance I2 and IJ and compete them against each other, and the winner produces a mutant that replaces the loser, and so on. So this process is in steady state, where at every point in time we're selecting a pair of individuals and competing them against one another. Okay, so this is our steady state evolutionary algorithm. Okay, let's write out some pseudocode for this now and then turn it into some actual code. So step 1, create a population of random individuals. Step 2, evaluate each individual in the population. Okay, and now for several iterations, we don't have generations anymore, just an iteration where a pair of individuals in the population are going to change. For several iterations, choose 2 individuals at random and make a copy of the more fit individual. When we make that copy, we mutate that copy, and then we replace the less fit robot of the pair with the mutant. That's it. Pretty simple, straightforward evolutionary algorithm. And at the end, we may want to show the best individual in the population. We want to see what this steady state algorithm actually did. Okay, so that's the pseudocode for our steady state evolutionary algorithm. I'm now going to take some time and turn this into some actual code. So if you want to follow along with me, I'm assuming the following things. I'm assuming that you have completed the phototaxis assignment, and when you have, you should have the following. You should have the quadruped, as I mentioned, that has evolved in 4 different environments. In the first environment, the light source is to the front of the robot. In the second environment, the light source is to the right of the robot. In the third environment, the light source is behind the robot. So what you're watching is one evolved robot played back 4 times in 4 different environments. And finally, in this fourth and final environment, the light source is placed to the left of the robot. As you can see, it's not doing very well in this final case. Okay, so I'm assuming that that's what you have, and by implementing that, you will have created a number of classes in Python. The first one that's going to be of interest to us is the environment class, this one here, and this, as the name implies, defines the environment in which the robot is going to behave. The other class that we're going to make a fair bit of use of is the individual class. And the individual class contains a genome, which is going to specify the behavior of the robot. And it's also going to store the fitness of the robot. And finally, it's going to contain a copy of the robot itself. Okay, so we're going to make heavy use of these 2 classes, the environment class and the individual class, in this project. Okay, as I mentioned, we're going to first implement the steady state algorithm, and that's going to serve as a base for step 2, which is going to be multi-objective optimization, or MOO for short. So I'm going to copy my current code base, and I'm going to create a new code base called MOO, multi-objective optimization. Okay, and I'm now going to navigate into that directory, and I'm going to start to modify the code base in there. So just remember, we're implementing the steady state evolutionary algorithm, but we're then going to turn it into multi-objective optimization. So let's create a new file called moo.py, and let's just put a single statement in there. And when I run moo.py, it doesn't do much at the moment except print 1. Okay, so what's the first thing we want to do? Well, we want to create an environment for our robot to behave in. So we're going to import, from environment, we're going to import the class called environment. And we're going to create an environment. So in order to create it, we have to go into that class file, environment.py, and see what we need for the constructor. We need to just pass it a single value e, which becomes the ID of that environment. For an environment that has an ID of 0, light source is placed to the front. For an ID of 1, light source is placed to the right, and so on. We're not going to actually use these multiple environments for now. We're just going to create a single environment in which the light source is placed to the front of the robot. Okay, so let's go back to moo.py. We've imported that. Let's create an environment called E, and we're going to assign it an ID of 0, which is the first environment. Light source is in front of the robot. Run our code. Doesn't do much at the moment because we're not using that environment. Let's also create an individual. We're going to have to first, from individual.py, import the class called individual. Okay, individual.py, what do we need? Same sort of thing. We need to just pass in a number which becomes the ID of that individual. Okay. So let's create an individual called I. We call the constructor for individual, and so we give that individual an ID of 0. Again, we run it, nothing happens because we're not using these two pieces. We now want to evaluate this individual in this environment. And just to remind ourselves of how to do that, if we go back to individual, we'll see that there's a function called start evaluation. This function expects an environment. We've already created that environment. That's fine. It requires an argument called PP, which is play in pause mode or not, and PB, which is to play in blind mode or not. Okay. So I'm going to just copy these 3 arguments to remind myself. I'm going to open and move again, and I'm going to call start evaluation. And I'm going to pass in these 3 arguments. My environment is called E. I'm going to play paused equal true and play blind equals false, meaning I don't want the simulation to run blind. I want to actually draw the graphics and see what individual I is doing. Okay, so now when I run it, I predict that I should see some random quadruped running around. Okay, it's paused. I unpause it, and here we go. Okay, that's pretty much what I was expecting to see. So we've got one individual evaluated in one environment. Okay, so far so good. But remember that we want to create a population of individuals. So let's do that now. So instead of creating a single individual, I'm going to define a new data structure called pop, which is a dictionary. The curly braces here tell me that it's a dictionary, and for I in range 0 to 10, let's create 10 individuals, and we're going to place those individuals in this dictionary. So the ith entry in the dictionary is going to contain an individual with ID I. Right? So we're creating 10 individuals now, and let's make sure that we created them all correctly by simulating each of them. So instead, we don't have I anymore. We have to call the ith individual in the population and start the evaluation of that individual in this environment. So far, so good. So back to our step here. We're creating a population of random individuals. This step. And we're then evaluating each individual in that population. Okay. Let's run our code now. You'll see that we get 10 that open up in parallel, and they're all in paused mode. So I could go through and unpause all of them, but that's a little bit clumsy. It's going to take me a while to do that. So let's actually kill these off, if I can. And we'll change things so that we start up each of the 10 individuals without them all starting in paused mode. Play paused equals true. Let's say play paused equals false. Okay, so when I run now, I get 10 individuals, and you can see that they're all behaving differently. So I know I have 10 different individuals that are each doing something different in this single environment. Okay. I started the evaluation, but I didn't wait for the evaluation to finish. I started up all 10 in parallel, and then the program finished. We also want to wait for these evaluations to finish and compute the fitness of each individual in its environment. So we create, again, a third loop now, loop over each individual in the population. And we want to compute the fitness. We want to wait for this simulation to finish, and when it does, compute the fitness of the ith individual in the population. So again, just to remind ourselves, if we go back to individual.py, here's our function called compute fitness, and we can see that it waits for the simulator to finish, collects sensor data from the simulation. We compute the fitness as the last entry in the 5th sensor. So let me just pause here. This might be a little confusing. Let's go, let's back up a little bit. I'm back at the online course here. Let's go back to the quadruped assignment and just remind ourselves what's going on with the quadruped. In here somewhere should be, right, a picture of what this looks like. Okay, so we have our quadruped here, and we have T0, T1, T2, and T3, which are the 4 touch sensors, one placed in each of the feet. And back in the quadruped assignment, you are placing a position sensor inside the robot. In this final assignment, phototaxis, we've replaced the position sensor with a light sensor. So let's actually go and look at that in the code. Instead of opening individual.py, I'm going to go down deeper into robot.py. Remember that when we create a robot, we create the objects, joints, sensors, neurons, and then the synapses. Let's go have a look at the sensors for a moment. Okay, so you can see that we send 4 touch sensors, 1 to each of the feet, and then finally we send a light sensor, which has a sensor ID of 4. It's basically the fifth sensor. Okay, so back to individual.py. When we compute the fitness, we collect the light sensor information, which gives us a vector of sensor data. That vector contains the value of the light sensor at every time step of the simulation. And we then just grab the final value in that vector. That's what the -1 inside the square brackets mean. And I'm just going to make a little bit of a change here. I was playing around with this earlier. We're just going to set the fitness equal to the final light sensor value, right? The robot should get as close to the light source as it can by the last time step in the evaluation period. Okay, so we've computed now the fitness. Let's go back to the top level here. We've computed the fitness of each individual in the population. Let's run it again. We see all our 10 robots being evaluated, one after the other. Notice that the program hasn't ended yet. It's waiting for these 10 simulations to finish. And when it does, the program ends. We've computed the fitness of all 10 individuals in the population. Okay, so how do we know what those are? Well, let's just print them out so we can actually see them. Print the fitness of the ith individual in the population. Okay. Off we go. Again, we create 10 random individuals, evaluate them, and when they finish, oh, this poor guy here flipped over. When they finish, we get back the 10 fitness values of each of our individuals in the population, and we can see that there's something wrong in the code here because all 10 are 0. So let's see where we went wrong. We are printing out, the fitness value. That's correct. Let's go back to individual.py and compute fitness. Aha, I see where we went wrong. For those of you that are not native Python programmers like myself, I grew up with Pascal first and then C. Fitness here, this is defined as a local variable. So the moment we exit out of compute fitness, we lose this value. In order to keep it, we need to call it self.fitness. And the self.dot means that this variable belongs to this particular class. Okay, so now it'll retain fitness, hopefully. Let's run it again. Again, we're evaluating 10, we created 10 random individuals. We're evaluating all 10 of them in parallel. And when they all finish, we print out the values of all 10 individuals. Okay, so we've finished this line. I can't do strike through, so I'll just leave it alone for a moment. Let's do bold, which means we've done that step. We've evaluated each individual. Before we go into this iterations, let's modularize our code a little bit. So first thing we want to do is initialize our population. So let's create a function called initialize, and inside that function we'll place this. So we're initializing our population. We then want to evaluate all. Let's actually call this initialize all, just to remind ourselves that we're initializing all individuals in the population. And we're then going to evaluate all individuals in the population. We start up the evaluation of all of them in parallel, and then wait for each to finish and compute its fitness in turn. And then finally, let's print the fitness of all of them. Okay, there we go. So initialize the population, evaluate the population, and print the population. Pretty straightforward. Run it again, we should see no change. Okay, there we go. Okay, so now let's go back to our pseudocode. Now we're going to loop through these four items one after the other, where we're competing pairs of individuals against one another. So we're going to create a loop now after we've evaluated the entire population for I in range 0 to, let's pick 5. We're going to do 5 iterations. I won't use, let's call it for iteration, so we won't get confused with I, which we've been using for the ith individual in the population. Okay, what are we going to do? Well, we're going to compete one against another. And just keep repeating that process over and over again. So let's define that function now. Compete one against another. Okay. And what are we going to do? Well, we're going to pick an individual at random. We're going to pick 2 individuals at random. So let's pick one. We're going to use the random library, and we're going to ask it to give us a random integer between 0 and the size of our population. We have 10 individuals, so we want a random integer between 0 and 9. Randint is inclusive, meaning it's going to pick a random integer between 0 and 9 inclusive. We've just made use of this library, so we need to go to the top of our code and import random. We haven't used it yet. And we're then going to pick a jth individual, also at random, from the population. You'll notice here that there is one condition we need to be careful of, which is we can't pit one individual against itself. So we need to make sure that j is not equal to I. So if it is equal to I, pick another individual. Right? So at this point, we should be sure that I and j are different individuals. Let's just print I and j for now. Let's not actually compete one against another, and away we go. Oh, I'm sorry, I'm going to do one other thing. I forgot to do something. Let me comment out this for a moment. Remember that up till now we've been evaluating 10 random individuals and then printing out their fitness. But as I'm developing my code, it's going to be a little bit cumbersome if I keep waiting for all these 10 to finish. So I'm now going to evaluate them in blind mode, which means just turn off the graphics. So in evaluate all, we have start evaluation, and play blind is equal to false. So let's change this to true, which means now everybody is going to be evaluated with the graphics turned off. And you can see how much faster things go with the graphics turned off. So here is the fitnesses of those 10 individuals that were just evaluated in parallel. Pretty quick. Okay. Okay, so we're competing one against one another. Away we go. Let's run our code. Okay, so we know what happened. We just evaluated all 10 individuals, and then the first iteration we picked individuals 0 and 6, then 9 and 7, then 4 and 7, then 4 and 3, 9 and 6, and so on. Okay, so we've got those we picked those 2 individuals. We now need to compare their fitness to determine who is the winner. We've now done this step. Sorry. We now need to figure out who is the more fit individual and who is the less fit individual. Okay. So we need to look at their fitnesses. So let's do the following. If individual I is more fit than individual J, so pop I.fitness, if the ith individual's fitness is greater than the fitness of the jth individual, then the winner is I and the loser is J. Otherwise, if population J's fitness is greater than or equal to I, then J is the winner and I is the loser. Yeah? Okay. Okay, so now what do we need to do? Let's go back and have a look at our pseudocode. We need to make a copy of the more fit individual, so which we can now just call the winner. Make a copy of the winner. So let's go back here, and we're going to now use, let's see, so the copy is going to be called, let's actually think about this. Let's just create a temporary individual called temp. And temp is, we're going to use the copy library. We're going to deep copy the winner. And we've just made use of the copy library, so we need to go to the top and import copy as well. If you remember, we've used deep copy before, which will copy not just the winner, but everything inside the winner, including its genome and its fitness. Once we have this temporary individual, we also want to mutate it, right? So we've made a copy of the winner. We now want to mutate that copy. Remember that if we go back into individual.py, in here is a method called mutate, and this changes the robot's genome, which will change its behavior when we reevaluate this new mutant. Okay, let's go back here. So we've mutated it, and the last thing we need to do, we've now mutated that copy, we need to replace the less fit individual, which is the loser now, replace the loser with the mutant. Okay, and we know that the loser is located at this place in the pop directory. And that's it. We're done. Okay. Now, how do we know that we've done this correctly? Well, let's print, after we've done this, let's print all again. So we initialize and evaluate and then print the initial 10 random individuals. We then compete one against another and then print the population again to see how it's changed. Let's change our iterations to only iterate once. We're only going to do one competition and then see, we're going to compare how the population has changed. Okay, so here we go. Let's run it. We can't really see where one begins and one ends, so let's go back and change our printing of the population. So after all the individuals have been printed, let's just print an empty line. Okay. So here's the initial random population, and here's the population after one competition has occurred. And if we look very carefully, we might notice that there's a difference. Let's see. Hard to say, right? How can we make this a little bit more clear? Let's make it a little more clear by printing out a little bit more information about each individual. Instead of printing just their fitness, let's print their IDs. Remember, again, if we go back to individual.py, each individual has its own ID. Okay. So here we go. Let's find the print function again. We printed the fitness, but let's first print the ID of each individual and then its fitness. Okay. It should be a little more clear now. Okay, so here we go, right? So individual 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and its fitness 0, 1, 2, 0. So we can see that in this case, one of the competitors was 0. That one was the winner, and it produced a mutant which inherited its ID number and also inherited its fitness value, right? We haven't evaluated this new mutant yet. So let's go back and see who it competed against. So let's print out the two individuals. Again, I took that away. Okay. So here's our initial population. Here are the two individuals that were selected for competition, 4 and 7. 4 has a fitness of 0.104, and 7 has a fitness of 103. So we know who should be the loser in this case. 7 should have lost to 4, because 7 has a lower fitness value than 4. And if we go down and look at the population after the competition, we see 4, 5, 6, and sure enough, a mutant of 4 has killed off individual 7. Okay, but we can see that our code is not quite correct because this is not actually the fitness of the mutant of 4, it's the fitness of 4 itself. So we are missing one step here after we replace the loser with the mutant, which is evaluate the mutant, right? We haven't done that step yet. Okay, so we need to compute the fitness of this new individual. So here we go. Compete one against one another, select the winner and loser, make a copy of the winner, mutate that copy, and then replace the loser with that copy. And we now need to evaluate the loser or the mutant, right, which is sitting in there now. So we need to start evaluation, and I've already forgotten what arguments we need for start evaluation. We need to give it the environment and some other arguments. Okay, so we're going to give it A. We're going to play, we're going to not play with pause mode turned on. Play blind is true. We're not going to see it. And then we're also going to compute, we're going to wait and compute the fitness of this new individual. Yeah? So now, after this step, we're going to know what the actual fitness of this new individual is. Okay, so now we've implemented all these steps, right? Let's see how this plays out. Okay, here's our initial population of 10 random individuals. We see that individual 3 competed against individual 9. And you can see that 9 has slightly higher fitness than 3, so 9 should have won. Let's check that. Here's 9, and we see in the slot where 3 should be, we have the mutant of 9. The mutant inherits the ID of its parent. And we've evaluated, and we see it gets a slightly different fitness than its parent. Excellent. Okay, there we go. Okay, so let's go back and have a look at our pseudocode now. It says to do this for several iterations. So now let's open up the engine of our algorithm now and let it compete pairs of individuals against one another and see what happens in the population. Okay. You'll notice that for most random individuals, fitness is sort of around 0.1, maybe 0.9, maybe you get lucky, 0.11, 0.11, 0.13. So you sort of know what the baseline is for random individuals. Up till now, we've just performed one competition. Let's do 10 competition. Actually, let's do 2 to start with. Let's sneak up on this. Okay, so in the first iteration, 6 and 4 competed against one another. In the next competition, 0 and 8 competed against one another. This was the state of the population after those 2 competitions. And we can see that now there's a new 0 in here, and there's a new 4 in here as well. So things are starting to change. Okay, let's remove this from the code. We don't need to print out the indices of the competitors anymore. So we're doing that in the function called compete. And let's also run 10 iterations now, 10 competitions, and print out the population after each competition. Okay, here's how things stand after 10. Not much has really changed, so let's really open things up and do 100 iterations. Okay. You can see what's occurred here. We have had one individual, or the descendants of one individual, individual 7, which have completely overtaken the population. If we scroll back in time, I'm scrolling back through past generations. If you were watching carefully, you would see that there was actually a competition between the descendants of individual 7 and individual 9, and eventually 7 won out and dominated the population. Okay, if we look at these values, we can now see 0.14, 15, and so on. So we're starting to get some evolution occurring here. Okay, so we're almost there. The last thing we wanted to do is to show the best individual in the population. So it would be nice, in this case, the best individual obtained a fitness of 0.151. Be nice to see how that robot actually behaves. So let's go back into our code. We've implemented all of the pseudocode. The last thing we want to do is show the best one, right? Okay, so let's define this function show best. First thing we're going to have to do is find the best. So in I equals find, let's call this best index. So this is the index of the best individual. Let's define a new function called find best. And then once we have it, we're going to start the evaluation of that best individual. We need to give it an environment to behave within. Play paused is going to be true. Give us time to bring up this window. And play blind equals false. We want to actually draw the graphics and see how this best individual performs. Okay. We don't need to compute its fitness because we're just interested in watching its behavior. Okay, we still have to define find best. Okay, let's do this by iterating through each individual in the population and looking for the one that has the highest fitness. So best fitness, we're going to start by setting it to lowest, a very low value. Best index is equal to -1. We haven't found anyone yet. And now for I in range 0 to 10, our population of 10 individuals, if the fitness of the ith individual is greater than best fitness, which is for sure going to happen for the first individual, we set the best fitness equal to the fitness of the ith individual, and we set the best index equal to I. So at the moment, I equals 0 is our best individual. Right? Okay, so by iterating over 10, we're going to find the index of the individual that has the highest fitness, and we need to return that index to show best. Okay, that should do it. Let's go back to our pseudocode for a moment. We now, at the end of our steady state evolutionary algorithm, we're going to show the best individual in the population. Okay. So here we go, we run it. We can see that 9 is now dominating the population and eventually kills off descendants of another individual. We have a pretty high fitness here. We can see some 0.2s. So before we play back this best individual, let's have a look at fitness values. We are going to be playing back this guy here, who has a fitness of 0.253. See how well he does. Not bad. Okay, clearly walking towards the light source. Okay, so that's the steady state evolutionary algorithm. Pretty straightforward. If we go and look back at the whiteboard here, we have a population of n individuals, and we pick pairs of individuals at random, and the winner kills off the loser by replacing it with a mutant offspring. That's the way it goes. Okay. Before we move on to multi-objective optimization, I'm going to just clean up my code a little bit. First thing I'm going to do is place some of these values in a constants file. So our population size, instead of having to type 10 every time, let's put them in a constants file. We already have a constants file on the go, constants.py from previous assignments. I think we already have defined a variable called pop size. So let's go through and replace numbers with pop size. Okay. First thing we need to do is import this constants file, and let's just call it C for short. And then we can find every instance of 10 and replace it with c.popsize. Same thing here. Same thing here. Here. Anywhere we see a 10 or a 9, because remember that random integers from the random package are inclusive. So we need to say c.popsize minus 1. Same thing here. Okay, so I think we've captured, no, not every single one. Okay, and we have another constant here, which is the number of iterations. So I think we actually have something called number of generations. Let's change this to iterations. And we have 100 iterations. That makes sense. So let's go back here. So we're going to iterate over c.num iterations. Okay, so excuse me. So now we can make changes to our population size and the number of iterations or the number of competitions we perform. Let's just for fun increase our population size to 20 to make sure this actually happens. Run it again. We can now see we have a population size of 20. We're running for 100 iterations. You should already notice a change, which is it takes longer for a certain lineage to dominate the population. It took quite a while for 12 to eventually kill off the last descendant of, in this case, individual 0. And the fitness values are actually lower here. We're probably not going to get somebody that did very, very well. Okay. We don't have anything here telling us what iteration we were on, so let's actually print out the current iteration number. So let's go back in here. Let's go to our print statement. And before we print the individuals, let's print the current iteration. We don't know what it is, so we have to pass it in. Call this, we're not going to print the first one. We'll print after the first competition, and we're going to pass in iteration. Okay, so now we can see number of iterations. We're counting up to 100. Okay, and away we go. Okay, so I think perhaps we only have 10 minutes left. So what we've done is now implemented this steady state evolutionary algorithm. Perhaps I will leave for next time the multi-objective optimization implementation. What I'll do instead is to talk you through how this multi-objective optimization process works, and then we'll start next time by actually implementing it. So let's go to the whiteboard. What I showed you before was sort of a picture of what's going on inside the population. Let's imagine I create another picture now, which is a single line, and this line is going to represent fitness. And I can then place on this line various points which correspond to the fitness of the individuals in the population. Maybe this is the fitness of individual 1. This is the fitness of individual 2. Let's imagine that individual 5 was the worst in the population at the outset, individual 6, and so on up to individual n. Right? So here I'm plotting the fitnesses of the individuals along a line. But remember, we might be interested in something other than just fitness, which in this case is uppercase L, or the amount of light that the robots collect, right? How close do they get to the light source? Let's imagine now that we're interested in not just evolving robots that get to the light, but that also maximize some other objective. So let's call this one T, which is going to stand for touch. We want to evolve robots that move towards the light, but don't leave the ground or jump or flip over. We want them to walk or keep feet on the ground at all times. So we're going to try and evolve individuals that maximize not just the amount of light they collect, but the amount of touch information that they collect. So move towards the light source, but keep on the ground as much as possible. So we now have a multi-objective optimization problem because we have two objectives, L and T. Let's imagine that when we create our initial population of 10 individuals at random and evaluate them, and any given random individual is only going to collect a little bit of light, and maybe it jumps around quite a bit and leaves the ground a fair bit, so it gets a relatively low touch objective as well. So we can now represent an individual in the population that's being assessed against two objectives as a point in the plane. We have 10 individuals, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hopefully you can see these points here. We've got 10 points which represent the amount of light and the amount of touch data collected by the 10 individuals in the population. Okay, now we're now going to try and evolve robots that move to this part of the plane. What we would like to get, and I'm going to draw this as an open circle because we don't have an individual that does this yet, an individual that collects a lot of light and also collects a lot of touch, or the touch sensors are usually 1, meaning the robot's feet are usually in contact with the ground. In theory, this point out here would be a robot that gets very close to the light, collects a lot of light, and stays in contact with the ground for most of that travel, meaning that most of the touch sensors stay at 1 rather than 0. How do we evolve these points to approach this theoretical maximum out here? The way we do that, let's just check on our time. We've got 5 minutes left. How do we do that? Well, we're going to use our idea from our steady state algorithm. By now that we've evaluated our 10, we're going to pick 2 at random. Let's say we pick this individual and this individual. Okay, so which of these is the winner and the loser? Well, in this case, I'm going to call this one I and this one J. We can see that I collects more light and more touch than J. So individual I is dominating. I dominates J. And dominates here is a very specific term, which means I is better on all of the objectives that we're interested in this case too. It has both more L and more T. So what would this look like in our code? This would mean that we have 2 conditions that have to hold, condition 1 and condition 2. And it should be that I dot L is greater than J dot L, right? I collected more light, individual I collected more light than individual J, and individual I collected more touch data than individual J did. Okay. So in this case then, in this example here where I dominates J, J would die and be replaced by some mutant of I. So we'll call this new individual I prime, right? And when we evaluate it, I prime is going to get some different L than its parent, and also some different T than its parent. Okay. So we now have this new point in our population. But since we killed off J and replaced it with I prime, we still have 1, 2, 3, 4, 5, 6, 7, 8, oops, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 individuals in the population. Okay, what happens if, for example, we were to randomly pick this individual and this individual? Now, which is the winner and which is the loser? In this case, we don't know because let's call this one I and this one J. We can see that J collects more light than individual I, but I collects more T than individual J. So one is better on one objective, and the other is better on the other objective. So these two individuals are known as being Pareto optimal. Neither is better than the other. Okay, so what do we do in this case? In this case, the competition fails, and neither kills off the other. So the competition just ended in a tie. Nothing happened. Okay, so we go back and now again pick two individuals at random. Let's say we pick this one and this one. We can see in this case that this is the loser and this is the winner. So the loser dies off. This one creates another one, a mutant, let's say, that lands here. Now maybe we pick this individual and this individual. You can see that this individual loses compared to this one, because this one is worse in terms of L and T. This one dies off. This one produces an offspring here. And if we repeat this process long enough, you can see what's happening is that our population is slowly moving up and to the right. And eventually, we hope we would get an individual that approaches this theoretical optimal, and we could then play back this best individual after a number of these competitions. That's multi-objective optimization, and I'll show you how to implement that in code next time. Okay, thank you very much, and we will see you next time.